All right. So we're back at it. We're getting close to finishing up the aromatic chapter here, but we've got I don't know, maybe two or so more lectures to kind of work our way through. But then we'll be done with this. But last time we were talking about this idea of activators and deactivators and how that tied with ortho and para directors and all those ideas were kind of tied up in electrophilic aromatic substitution, but I did tell you there's another mechanism that's kind of part of all this shenanigans, and that's nucleophilic aromatic substitution. And so that's what we'll start to talk about here. So nucleophilic aromatic substitution. Whoa. How amazing would it be if I actually had editing skills to edit these videos? Anyway, and so nucleophilic aromatic substitution is pretty much exactly what it sounds like. We're going to be bringing in a nucleophile, and it's going to substitute at a part of the ring. Okay, so immediately when I tell you guys about substitution, you guys might be thinking something like, SN1 and SN2, and that's a fair thought, right? We've talked a lot about SN1 and SN2s and the related mechanisms, but it's not really like that. And I say that here, and then I'm going to show you guys the mechanism. You're like, no, he's wrong. It's SN2. Well, it's not really, okay? And I'll show you guys why. So you'll just have to believe me for the minute, right? But I promise it's not really like an SN2. Okay, so we will be substitute a halide for a nucleophile. Okay, so I just told you guys that it's not SN1 and SN2, and then I tell you, but we're going to substitute a halide for a nucleophile. All right, so I don't think I've done much to convince you guys at this point, but don't worry, we'll get there, right? We'll make it all come together. Here's where it deviates a little bit. Fluorine. Well, I should say fluoride/fluorine. Let's erase here. Come on, pen. Fluoride/fluorine, right? Whichever one you want to think about in this case, is the best leaving group in this case. Now, this is unusual for a couple of reasons, and I'll probably mention them as we go along. But to begin with, how many times have we seen fluorine chemistry so far? That's right, really once, right? We've only really seen one reaction with fluorine. Can you guys think about which one that is, right? We used it in one case that I can think of, and it's actually a pretty important use for it. But the point being that really we don't talk much about fluorine chemistry in the undergraduate organic chemistry course, and the reason for that is because fluorine chemistry is kind of a different beast. It's extremely useful chemistry, but because of the nature of fluorine and fluoride, it does have some very unique reactivity with it. And so this is one of the rare cases where we'll talk a little bit about it, and we will use it to kind of start to build some larger molecules there, right? But just keep that in the back of your mind. So fluorine and fluoride is the best leaving group, and consequently, iodine, right, and iodide are the worst. Now, I'm not saying that they don't react, it's just that they're slow. They're a lot slower. Iodine and iodide are a lot slower to do this type of chemistry than the fluorine and fluorides are, okay? All right, so there's that. What else do we need to think of here? Let's see here. How do we want to? What's the best way we can say this? Well, let's talk about a nucleophile here real quick, right? Do we all remember what a nucleophile is, right? That's some kind of electron-rich species. It could have a negative charge, okay? Right? Could be negative. But actually, right, we'll find that amines So ammonia, for instance, amines, are actually really good at doing this reaction, and that's darn important, okay? We'll talk about a little bit about how we can start to build together some larger molecules using amines here. But, really, when we're talking about a nucleophile, we're just talking about something that's got a negative charge, right? There are actually two mechanisms here, okay? And the two mechanisms, right, what's going to be different about it is the reaction conditions that they are in. One of these mechanisms that you guys are going to be far more familiar with than the other, okay? But we need to we'll introduce the new one first, and then we'll go look at the second one. The one that we're going to talk about in this video, the mechanism in this video, is going to be the more let me see how I should say this. It's going to be the more useful one. It'll be the one that we can actually practically use, and you guys will see why as we kind of finish up and go through both of them there. Okay. All right. Oh, sorry. One more important point here. We're going to see some carbon ions, right? Now that's going to be pretty unusual, okay? We haven't seen too many cases, right? Really only one or two where we've run into some carbon ions so far, but we're going to be looking for carbons with lone pairs and negative charges, all right? But these are going to be just, a different type of intermediate for us, right? Kind of like carbocations. And so for our purposes, we're going to essentially just treat them the same way, right? We're going to have to look at stabilizing them and dealing with them and spreading them out and all this kind of stuff, right? So we will take a peek at what happens with all these here, okay? So just a couple of little bits of information there before we get started with taking a look at what in the world is actually happening here, right? Okay, so what is going to be happening here then, all right? So let's take a look at Mr. Generic reaction then, right? Let's say we got a benzene ring, okay? And we're just going to start with a simple example here, right? And we'll, as we build this up, right, we'll come back and correct some things here, all right? Let's do this. Okay. All right, so let's take a look at this guy here. If I've got my buddy, let's say nitrofluorobenzene here, right, or para-nitrofluorobenzene, and if I take this, right, and I reacted with a nucleophile, okay, so let's start with Mr. Generic nucleophile then, right, so let's call it nuke, okay. If I do this, right, and I mix these things together and I let it, go about its business, at the end of the day, this is what I'll have, okay? I'll end up swapping in my nucleophile for where that fluorine is. Okay, that kind of makes sense. Maybe I can see what's going on here. How is this not SN2 again? I know. Okay. But let's say that as a counter argument here, right? Let's say as a counter argument here, I'm trying to figure out this mechanism. And so being an intelligent chemist, I start to probe some of the things that I know about here, right? If I take the paraderivative, and I say, all right, well, what happens when I compare, okay, these two reactions here, okay, so let's say we compare these two reactions. This guy up here, this went pretty fast, right? This reaction here went pretty slow. So pause here for a second, say, okay, right, I'm setting up an example for you guys to figure this out for yourself here, right? So take a look at these two generic reactions, right? We have some kind of nucleophile attacking essentially the same substituted ring, but in one case we had a very fast reaction, right? In one case we had a very slow reaction. So take a pause here and see if you guys can figure out what's going on. Can you guys propose a mechanism for this? Okay. All right. So hopefully, whenever I ask you guys a question of, see if you guys can figure this out or think about it, the first thing you guys should do is to go through and draw the mechanism, okay? Or propose a mechanism, or think about what's going on. All right, so I'm going to take the top reaction there, okay? And let's propose a mechanism for this. This is what we had. Okay. So what do we know about nucleophiles? Well, they've got a negative charge and they're on the hunt for something positive. All right. Well, where is my positive charge? Well, the positive charge is going to be on that carbon that's attached to the fluorine there. Okay. So I know. Bear with me here for a second. Okay. This is going to be step one. Now, for those of you guys who didn't pause earlier, when I asked you to, propose an idea for the fast and the slow, pause now, right? Go back and now see if you can explain why one is fast and why one is slow. Okay? Please go try this. It's like I said, you otherwise you just listen to, Dr. H's explanation of organic chemistry, right? And that's great, I'm not too bad at this, but, really the whole point comes when you guys can explain it for yourself, okay? But here's what we should be looking at, right? So after the first step here, where we have a nucleophile, right, what do we notice? Well, now we got a negative charge on our ring. Let's pause here for just a second. Is this negative charge really any different from our friend Mr. Carbocation that we've dealt with all along? Well, sort of the answer is no, right? We've got some kind of charged intermediate that we got to spread out, okay? So we want to try and draw some resonance structures. We want to try and move this thing around, all this kind of stuff, right? And so that's exactly what we can do, right? We can start to draw some resonance structures here. And hopefully, you guys will start to see what the deal is. Let me finish drawing some of this in, right? Now let me pause here, right? So what do you guys notice? Okay, so very similar to how we explained orthopara versus meta-directing in the electrophilic aromatic substitution. Right here, right? Okay, we've got a positive next to a negative. So what we can do, right, is exactly what we could do previously. We'll slam down a pi bond and kick this up, okay? And that will leave us, let's see, here, got all this, that's a negative. We've got, let's see, a negative here. And we still have a positive here. We've got that, and we've got that. Okay. I think I got everything in there. I didn't leave anything out. All right. So we can now draw an additional resonance structure because we've got that nitro group on there, right? We can share that negative charge into that, ancillary group there coming off of the ring. Okay. We can push that negative charge onto an oxygen with a negative. That's pretty darn good, right? All right, so let's finish this up. Okay, I'm going to draw a bunch of arrows at once. You guys ready? Okay. 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 So pause here if you want to. Actually, no. Even if you don't want to, pause here. Okay, and see if you guys can draw the product that I have after all those arrows. We got this, got this, got this. Trying to fill in all the colors properly here. So we got a nice colorful, whoops, a nice colorful set of aromatic rings. This was green. This was blue. Got that. Okay. And there we go. So how is this not an SN2 reaction? Well, hopefully you guys can see at this point, right, that remember an SN2 reaction, it's a concerted reaction where the nucleophile comes in and displaces the leaving group. But here we've got the shenanigans going on with the ring, right? We've got to stabilize charges and delocalize things, and we make and we move pi bonds and all that kind of stuff together, right? But this is one of the mechanisms for nucleophilic aromatic substitution. Okay. Question. What's the rate determining step? Step. Okay. Pause and see if you guys can figure out what the rate determining step is. Remember, this was important when we were talking about our electrophilic aromatic substitution, when we were talking about activators and deactivators and all that kind of stuff. Do you guys remember what it was in the electrophilic aromatic substitution? Because the answer is going to be the same here, right? The rate determining step is where we break the aromatic ring. Okay? So really, right, when we break the aromatic ring, that's going to be our rate determining step, right? Now, if you think about that again, we should say, well, that makes sense. We're bringing in a nucleophile to attack a pi cloud to break an aromatic ring. That doesn't sound too easy. And it's not, right? It's not easy. So let's go back up here. Why is one of these fast and why is one of these slow? Well, we did the mechanism for the fast, right? Can you guys figure out why the slow mechanism or the slower reaction there is going to be slow? I think you guys can. How would you answer this? Well, the answer for that would be you're going to have to draw the mechanism for it, and then use that to rationalize why the slow reaction there is going to be slower. But I'm a lazy man. I want this to go even faster. How could I make this reaction go even faster? Well, let's add some more nitro groups to it. The more nitro groups I can add, right, to my ring, so if we go crazy and add a bunch of nitros, this reaction is going to go even faster. So we'll call this scientifically super fast. All right. And now, of course, I'm being a little bit disingenuous, I guess would be the best statement here. Because we got to stop and think. Okay? It's not easy to get 3 nitro groups onto a benzene ring. Why? Why is it not easy to get 3 nitro groups onto a ring? Does it mean it's impossible? No, I didn't say it was impossible, right? But it's not easy either, so, why would that be the case? But anyway, the point being, the more nitro groups, the more electron withdrawing groups you put onto the ring, the faster this mechanism is going to proceed, okay? The more electron withdrawing groups you put onto the ring, the faster this mechanism is going to proceed. And there you go. That is the basics of, right? That is the basics of electrophilic aromatic substitution. Why is this useful for us? Well, okay. If I take this and I let's say I bubble in some ammonia, or I put into liquid ammonia and all this kind of stuff, right? I can actually, whoops, this is a way that we can add amines directly to the ring itself. That's pretty darn useful, okay? We can substitute in alcohols also. So if I have this, if I've got a nice withdrawing group there, I can even bring in some alcohols. Oops, I'm sorry. Meant to do it like that. I can even add some alcohols in there. That's one way of doing this. And actually, in the biochemistry world, right? In the biochemistry world, this is a very useful mechanism that they use to label peptides and proteins. There's certain like fluorescent agents and stuff that they can put onto the. I don't really know too much about it, so I'm not trying to be vague on purpose. But I know this is a common. I forget the name of the reagent off the top of my head, but they use this mechanism to label certain peptides, and so then they can track them through biological systems and things like that, right? But this is what we can do with a deactivated benzene ring, and that's one of the key parts of this, right? We need electron withdrawing groups on the ring for this to happen. It is very important to have nitro groups and electron withdrawing groups on the ring itself. Why? Why is it important to have electron... Whoa. I'm sorry about that. It's kind of disorienting. But anyway, so why is it important to have electron withdrawing groups on the ring? Well, there's a couple of reasons for it, right? First, right, we're trying to bring in a nucleophile, so something with a negative charge, or a partial negative charge at least, right? And so if we have a very electron-rich pi cloud, right, this reaction is just not going to work, right? Negatives are going to repel negatives. The second reason is to stabilize the intermediates there. So when you're trying to set up a nucleophilic aromatic substitution, make sure that you've got electron withdrawing groups like nitros, or nitro rings, or excuse me, nitro groups are the preferred, to be honest, right? Make sure you've got nice nitro groups somewhere on your ring to start to, let's say, give the opportunity to do nucleophilic aromatic substitution. Okay? But that's it. At the end of the day, the mechanism here isn't all that different from electrophilic aromatic substitution, with the important part being, right, the rate determining steps are similar, right? Breaking the aromatic ring, right, is a rate determining step in both cases, right? The selectivity, right, the speed of the reaction is determined by how we can stabilize the intermediate, the carbanion in this case, versus the carbocation in the other. All right. So I'm not trying to paint them as too similar, but there are similarities between the two mechanisms there. Okay. So there you go. That's the overview of nucleophilic aromatic substitution. In the next video, we'll talk about the next mechanism, and then in our problem session, we'll start to do some more examples for these. Okay.